This is Fruit Ninja, a game where you try to slice every fruit on screen while avoiding bombs. Every time a fruit falls off the screen without being sliced, you get one of these X's. If you collect 3 of these or slice a bomb, you lose. The problem with Fruit Ninja is that you normally need to use your hands to slice the fruit, but my hands are kinda sore from coding all the time, so I'm gonna code something to play it for me. I started working on this project when I was recommended this video called Using Image Recognition to Destroy Fruit Ninja by CodeNoodles. In this video, he also tries to tackle this problem. His solution was to use a mean filter, where you take the average of a subregion on the screen and compare the average to known fruits. Using this, you can get a crude image recognition to detect fruits and bombs. The problem with this is that there are many different edge cases and scenarios that are very difficult to handle. This problem appeared in CodeNoodles' video when the program mistakes a bomb for a fruit. With this in mind, let's take a step back. In Fruit Ninja, the fruits you need to cut are actually 3D objects that are constantly rotating, so a single fruit can appear differently. This means you can't take an image of a fruit and search the screen for this image, as there are nearly infinitely many different rotations that the fruits can be in. And, on top of that, there are many different fruits. You could search the screen for anything that is a different color than the background and compare it with the fruit's colors, and this is similar to the mean filter that CodeNoodles used. But if you were to do this, you'd quickly run into many issues with false positives. As you can see, there would be many cases that would be difficult to handle, with fruit splatter, already cut fruit, and fruit being behind text being a few examples. We want to avoid these complications as much as possible. That's why I'm going to be using a convolution neural network, or CNN, to detect the fruits and bombs on the screen. Don't worry, you don't need to know what this means. I'll explain everything you need to know. I am going to be only scratching the surface of how CNNs work, but if you want more in-depth details, I've included a link in the description that I believe is a good source. A CNN takes an image as an input and outputs predicted bounding boxes and labels for each object in the image. For a CNN to know what bombs and fruits are in this image, it first needs to be trained on similar images. To train a CNN, a dataset of correctly labeled images is needed. And of course, that means I get to sit down and label some images from Fruit Ninja. For this labeling process, I'm going to be using a website called RoboFlow. This website makes it easy to label images and export the data to be used in training a CNN. I'm going to label every solid, uncut fruit as a fruit and every bomb as a bomb. For the CNN to be accurate, many images need to be labeled with precise bounding boxes. To put it into perspective, for this project I labeled over 3,500 images to get the model to the accuracy I was looking for. After labeling the images, a CNN can now be trained on this data. Remember, a CNN is a convolution neural network, but there are many different CNNs. You can think of a CNN like the word car. There are many different cars that are good for different things. For example, gas mileage, cost, speed, etc. This same idea can be applied to CNNs. There are many different CNNs that are good for different things. But in this case, it's things like accuracy, speed, or size. For this project, I am going to be using a CNN called YOLO V8. YOLO is a CNN that stands for You Only Look Once. I am choosing this model due to its accuracy, speed, and the documentation surrounding it. Training a YOLO model using the labeled data gives us a custom CNN that is trained to detect fruits and bombs. Here are a few images that I passed through the model, with the left image being the input and the right image being the labeled image from the model. This process of passing an image through a CNN is called inference. As you can see, it's doing a pretty good job at detecting the fruits and bombs while ignoring the background, splattered fruit, and already cut fruit. The problem with this is that the inference is slow. The primary reason for no one using a CNN to do image recognition to play Fruit Ninja is because of the complications in using a CNN and, of course, the slow inference. If I use my CPU for inference, it takes 2.9 seconds. But this speed can be greatly improved if I use my GPU. Using my GPU, it takes only 0.018 seconds, or 18 milliseconds, which is equivalent to 55 frames per second. This means if inference was the only part of the program, it could play at 55 frames per second. But this isn't the only part of the program, meaning we want to speed it up as much as possible. The speed can be increased further by changing how the model is stored and used in the computer. Currently, the model is in a PyTorch format. This format is good as it's very flexible, but just by changing this to a TensorRT format, the GPU inference speed decreases to 10 milliseconds. This means if the entire program ran at the speed, 100 frames per second could be processed. Now that a fast way to infer new images has been created, a main program must be created. This main program needs to take a screenshot of the game, infer the images to find the fruits and bombs locations, create a path between the fruits that avoids bombs, and move the cursor along this path. This all needs to be done extraordinarily quickly, because if it takes too long, the fruits and bombs will move, making the planned slicing path no longer correct. I am using Python for this project, as it has lots of support for image recognition models and simplifies this project's complexity. But the problem with using Python for this project is that it can be slow, which makes this real-time task difficult to complete, and means some unique solutions must be used to speed up the program. The first step in creating this main program is to capture an image of the screen. There are many modules that can be used to capture an image of the game, but I am using a module called BetterCam, as it is the fastest way to capture the screen that I tested. To capture the screen, a camera object needs to be created. Once a camera object is created, the screen can be captured using Grab. The Fruit Ninja game window does not fill my entire screen, but I want the screenshot to be of only the game. So a region of the screen I am interested in is included in the method call. I am also calculating the game window's location once and caching it to save time. Now, with the image of the game, the previously custom-trained YOLO model can be used to infer the object's locations. The arguments used do the following. Screenshot is the image of the game that was captured. Device is what device to use for inference, and in this case, it's the GPU. Verbose means if information should be printed to the console about this inference. Conf is the minimum confidence threshold for a valid detection. Int8 makes the inference use smaller sized integers. This helps increase the inference speed. And image SZ is the size of the image the model should use during inference. After inference, the model returns results that contain information on all detected objects. For every detected object, 5 values are returned. These values are the object's types, aka whether it's a fruit or a bomb, and the x-coordinate, the y-coordinate, the width, and the height of the object. The coordinate values are normalized, as if they are for a 1x1 image. By using the object type and its coordinates, all the fruits and bombs on the screen can be converted into an easier format to work with. To keep track of the game information, a class called Game is created. In this class, I can keep track of common global values. The self.bombs and self.fruits are representations of the current bombs and fruits on the screen. I will go more in depth on how these work later. The self.maze size is the size of the maze that the pathfinding algorithm will use for finding a path between fruits. In this case, it will use 200 by 200 pixels. This smaller pathfinding size is used as it can still find paths around the bombs while being faster than searching a map the size of the entire image. The self.size multiplier and self.bomb size is used to create a more conservative representation of the bombs. Because the bombs are sometimes occluded by something else, if I were to use the previous widths and heights of the bombs, one could accidentally be cut if it were to be behind something else. So a set bomb size is used instead. The self.min fruit height is the height a fruit must be at to get detected as a fruit. This is to prevent cut fruits and bombs at the bottom of the screen being mislabeled as a fruit. The self.min start slice height is the height a fruit needs to be at to have the program slice it. This is to try to get more fruits on the screen for better combos. There is more in this class, such as methods to simplify extracting information using the fruits and bombs information. I will go more into the methods later. To keep track of the fruits, another custom class is created, which has the x, y, width, and height of the fruit. Using the information extracted from the screenshot, a fruit object can be created using this class. To keep track of the bomb's locations, a different solution is used. Because I am pathfinding between the fruits to slice them in a combo, I'll be testing if a point is colliding with a bomb very often. This means I want to have a way to quickly check for this collision. To do this, a NumPy array is used. A NumPy array is similar to a Python list, except it is much faster in some use cases. To keep track of the bombs, the NumPy array is designed so each column of the array is a different detected bomb. The rows of the array are different values of the bombs, which are its x and y location, the x and y location of its corners, and the x and y locations of its corners if it were to be scaled by the maze size seen earlier, which in this case is 200. Another method in the game class is responsible for updating the fruits and bombs location with every frame. One thing to note is that fruits are only added if they are above a certain height of the screen and not overlapping with the bomb. To detect fruit collisions with the bombs, the corner coordinates of all the bombs are compared to the fruit. And if the fruit coordinates are inside the bomb corners, it must be overlapping. Now that there is a simple representation of the fruits and bombs that can be used in the rest of the program, a path between the fruits can be created. To find a path between the fruits, a search algorithm called A* can be used. In simple terms, this algorithm starts at a start location, which in this case is the first fruit, and tracks all of the adjacent pixels, which I'll be calling its neighbors. For every neighbor, an f-score is calculated. The f-score is the sum of the current distance and the predicted distance. If these neighbors are not in a bomb and not outside the maze boundary, they are added to a list. The neighbor with the lowest f-score in the list is selected as the next pixel. This process of adding the neighbors, then picking the next pixel, is repeated until a path is found, or every part of the maze is searched. The predicted distance for the f-score is found by taking the Manhattan distance between the current location and the end location. The Manhattan distance is the distance between two locations assuming you are unable to go diagonally. So in this image, it's the red, blue, and yellow lines, all of which are equal to 12. This distance is equivalent to taking the sum of the difference in the x and y coordinates, similar to the red line. By repeating this process of finding the neighbor with the lowest f-score and assigning an f-score to its neighbors, a shortest path can be found between the two locations. After implementing this algorithm, it can be tested with the fruits. As you can see, the search algorithm builds a path from the lemon in the middle right to the watermelon in the bottom middle. Now that the A* algorithm is complete, a loop through all the fruits can be used to chain the paths between the two fruits together and get a single path that goes through all the fruits and avoids bombs. This method first checks if there are any fruits. If there are not, an empty path is returned. Then it checks if there is a fruit above a minimum height or a pomegranate on screen. If there aren't any valid fruits above the minimum height, an empty array is returned. If there is only a single fruit, then a path with only that location is returned. If there are two or more fruits, paths connecting all the fruits can be found and combined. With these steps completed, the next process of cutting along the path can be completed. To cut the fruits in the path, a module called PyInput is used. I'm using this module as it is the fastest module that I could find for controlling mouse movement. The mouse is first moved to the first pixel location in the path. Once the mouse is on the first fruit, a circle is drawn to cut this fruit. This is to cut fruits that are by themselves on the screen. After this, the mouse is moved along the path that was calculated earlier. This process of taking a screenshot, inferring the image, pathfinding, and moving the cursor is repeated as fast as possible. When doing all of this, I was able to get the program down to 13 milliseconds per frame, meaning it does all of this at 77 frames per second. Now with the program done, I can show you some results. In the top left corner is a video of the game. This is the screen you would normally see if you were playing Fruit Ninja. In the bottom right corner is a video interpretation of what the program is seeing. Remember, the program doesn't normally create new images to play, it instead uses the bounding box locations extracted from the top left video, but I use the bounding box locations to create images of what the program is interpreting. By doing this, you can see the program actively labeling the video. The FPS counter in the bottom left of the video is not the program speed. This is the FPS the Fruit Ninja game is running at. These videos are both real-time videos of the program playing the game. As you can see, it's detecting the fruit, waiting for it to be above a certain threshold of the screen, and once it is, it cuts it. One thing worth mentioning is since I took the frames from the program and made a video from them, the bottom right video sometimes becomes out of sync. I've tried to keep it in sync the best I can, but it's not perfect. I'm going to let the video play and chime in whenever there is something to know. Unfortunately, due to the fruits being too close to the bombs when they were above the set window threshold, they didn't get cut. So in the top right corner of the video, you can see that there are 2 X's already. Thankfully, in Fruit Ninja, after 100 points, an X is removed. So once a score of 300 is reached, one of the X's will be removed, and at a score of 400, the other will be. At a score of 500, the game starts to noticeably increase in speed, making it more difficult for the program to play. At a score of 1000, the speed of the game is much more challenging than before. At 1500, the fruits and bombs are on the screen for only a fraction of a second, meaning the program must be very quick to keep up with this speed. Remember, all of this is being done in real-time speed. At a score of 1,835, the program fails to recognize the fruits in time and loses. If you liked this video, make sure to give it a like and subscribe if you want to see more videos by me. Thank you for watching, I'll catch you in the next one.